What's up guys, it's me again, chemical engineering guy, going to see this topic which is mass balance equations. And we've seen before mass balance in 1 unit, mass balance in 2 units, and mass balance in many units. Now, this is with no reaction. And what I want to show you here before is what is the recycle or bypass. You have no idea what I'm talking about, you should go before the videos, check some videos, previous videos, see what I'm talking about, because these guys here, recycle and bypass, are very important, especially recycling. So what I am talking about, let's do this diagram. There's a reactor and there's a separator. We have one feed that's going in. Maybe you feed the reactor and it reacts, but it doesn't react that much. And then you separate your product and you see that you don't have the desired quantity. So what normally people, or how to say, many industries do is, okay, I'm going to pass it again just to check if it will react more, which makes sense, no? You are recycling and you will have more. So before you had, I don't know, 3 of them here, one goes up. Well, actually before they 3 go up. But now I will say I just want to send one part here and I want to make those 2 moles to react here. And it helps, it actually helps. You will see later why in mass balance. I actually have one mass balance example in which you compare a recycle and a current with no recycle, a process with no recycle. So this one is good and this one is very terrible with no recycle. So simply recycle, as this is the definition, it's a product stream of a unit being returned to a previous stream or unit. I mean, here is a stream here, but I could actually make it and take it to the reactor. Whatever the process thinks it's better. Maybe you need to heat here, so that's why we're going to give it in the feed before. Maybe the feed needs to be cold and this product is cold, so that's why they mix it before and then they throw it to the reactor, etc. That's for recycling. Now bypass is way another thing. It's similar, but I think it's easier to answer because if we have a feed here and we have this unit, what we're going to do is, okay, you get some feed, but we're going to also have a little bit of feed in the product. And you will probably tell me, why do we do that? Because it doesn't make that much sense. Wouldn't be better just to have a splitter and something goes and the other just not goes? Well, the problem, or the typical problem one is, I love this example, is the one about juice. They have this juice, it's a normal juice, they want to concentrate the juice. So they are going to evaporate water and you will finish with a juice amount, I mean orange amount or concentration bigger. But the problem says that you don't have enough, I don't know, flavor. The flavor is artificial. It's all the good things went with the water, all those stuff you don't account for. So what the engineers do is simply, okay, we're going to do this, but we need to add a little bit more of normal juice so it will taste like juice, which is good. So now, once again, the definition, bypass, it's a fraction of the feed which is diverted around the unit and combined with the output stream. This is the output stream, this is the feed stream. So technically this flow goes backwards and this flow goes forward. Here's an example of recycle. Please give yourself some seconds to find the recycle, even minutes. Pause it. Going to wait for you. And okay, hopefully you're done. We're going to see where is the recycle. Actually, it's here. This is the recycled gas. Sorry. So let's analyze this. We could use this 1 unit. So you feed the hexanized naphtha, you feed it and then you heat it. And once it's heated, you can go through this series of fire heaters. And then what you're going to do is bring it here. It's a gas separator. You either go take this hydrogen, maybe the hydrogen you're producing, but you also need hydrogen to the process. Why? I don't know, maybe it helps your reaction. Maybe you need to have hydrogen here. I don't know, but the hydrogen must be returned, and that's what they're asking you, and that's why you are recycling. Now, bypass is a little bit more difficult to find examples, but we're going to give this. So these are the bypass, because we have these here. This guy here is not going through heating and not going through here and separation and blah 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 blah. It's going directly to the distillation column. And this one guy here also. But pay attention here, please. You will have that you are sending directly to the feed well, whereas this one is going through some processes here, process here, process here. So that's the difference. Bypass goes through or passes or jumps equipment. Now, the obvious question is why recycle? I mean, chemical process recycle. Now, the important thing, we're not seeing this right now, but for chemical reactions to increase conversion, you need to recycle. So if you have a conversion XA, you have, I don't know, 10%. If you will just simply recycle that, maybe it will react to 20%, who knows? So that's why they do it. Sometimes they need to recover a catalyst, which means money, because catalysts in general are expensive. So they prefer to recycle and reuse it rather than just throw it away. Also, there are many processes in which you need to dilute the process stream. You know, a stream is so strong, I don't know, if you have sulfuric acid is at, I don't know, 98%, and you want, or your pipeline just accepts 20%, you got to dilute that. So you're going to recycle, which means you're going to increase the flow and decrease the composition, normally. Also, and this is very typical, I didn't knew it before because I didn't care that much, but once you're in a chemical plant, you're controlling reactor, you're controlling, I don't know, many processes, you are always expecting that temperature, pressure, levels are the same. If they are not the same, it means something is wrong. And why is something wrong? I don't know. But the control process will help us. And how do we do that? Normally you do a recycle to, I don't know, this is a huge recycle compared to this stream. So the temperature of this is, I don't know, 500. And the temperature of this is, I don't know, 100. You will, because this is too big, this current will not make nothing. This current will laugh, like, oh, you're so small, my temperature will stay the same. So that's one example. And finally, the recirculation of a working fluid. Sometimes refrigeration, you will need refrigerant, and in plant generation or generationary plant, you need steam. Steam or water will be always flowing in the process. Now, bypass is a little bit difficult to explain. It will increase properties of the product by adding raw material, like the juice I told you before. You add good flavor. The operation unit does not work as desired. You have this unit, but I don't know, you want to top max. So you are top, I don't know, maybe the max is 100 kilos per hour and you have 120. Well, if you put those 20 in here, you will have, of course, spill. The fluid will spill and you will destroy the tower and a lot of security hazards, etc. So what you're going to do probably is to take it here and maybe eventually make it flow or send it to another one. And once again, process control variables. I don't know, maybe you want a different composition plus you want another temperature or pressure, so that's why you send this current or stream here. So nice. Let's see an example. This is kind of large. 4,500 kilograms per hour of a solution of K, let's call this K, by mass is joined by a recycled stream of 36% of K. Nice. The combined stream is fed into an evaporator. The concentrated stream leaving the evaporator contains, okay, we have another one of K. This steam is fed into the crystallizer. Okay, we have a crystallizer, which is cool, causing crystals to come out of the solution. Crystals mean solids, so guys, we're going to work with solids. Take care. And then the mass, the crystal account. This is super important. Crystals count 95% of the total of the filter cake. What's a filter cake? Filter cake is simply the solid part of the filtration. The solution that passes through the filter is also, okay, another concentration of K to the recycle. Of course, they need to be the same because it's the same product. Nice. Now, we're going to calculate the rate of evaporation, the rate of production of K solid, the feed rates of the evaporator and crystallizer must be blah, blah, blah. Okay, now we need the recycle ratio, which is exactly the mass of recycle divided by the mass of fresh feed. Good. And suppose there was no recycling. Okay, we're going to see what happens when we do not recycle. Nice. Let's do it. What are we going to see? Let me show you the diagram. Once again, we're going to feed K, which has 33% percentage. The other one is water. We're going to mix it with the recirculation fluid. And then we have this feed. I put E just to know it's the entrance to the evaporator. It has a composition I don't know and a composition I don't know of K and water, so that's why I use these variables. Evaporator means that I am going to take out water. Nice. Now, the feed in the crystallizer, that's why I put the C here, we know it's data, so that's nice. And they tell you PC, I will be calling the solid crystals, and PS is the non-solid solution. The crystallizer will have some product here before. As you can see, of course, it's the same composition because it's the same solution. The only thing is that we're going to recirculate this one and we are not going to recycle this one. And besides, they tell you, note 1, 95% of the mass of the cake is sent here. Good. So now we got to calculate Q, P, F, Fe, Fc, and the relationship. Good. Let's do a mass balance from node 1. Remember that PD is essentially just the addition of these two guys. So PD is equal to 5% of PC plus PD. PC could be, this is like liquid and this is the solid, etc. And you find a relationship between PD and PC. I just write it down. You cannot solve it further. But just to let you know, PS equals C and D, this way, which means the K and the water. Good. Now, let's do a mass balance globally in all the equipment. Hopefully you know, or if you don't know, let's do our system. Recycle is never included. We actually just have inlet of F, outlet of Q, and outlet of P. Yeah, which is here, F equals Q plus P, C, and PS. And the same balance, but now we're going to do the balance in K, which is exactly the same, just add the X's, which means composition of X. No, composition of K. We have this, yes. This is common sense, it's water. You cannot have dissolving water, so it is 0. This is solid, so it's good. And this is the solution. Now, we're going to substitute 1 in 2, which is this here. It's going to come here, which is exactly what I am doing. 1500, this is this. PC is here. This strange number comes from here. And PD, I'm telling you, is this. So we just insert this here and solve. Let me just do this. We have this and 0 and here and PD it's equal to PC. So nice. We just have one equation with one unknown, solve for PC, and you get this value. Good, we have PC. Actually, you could go for more, but let's do this. We are going to substitute 3 in number 1, which is the simple one, is this one. So substitute this, and you will get now the value of PD. Nice. Now, we need to find water, and it is actually easy. We now know P. P is the product, the general thing that is going out is the solution plus a solid. So we add these two, we add F. We don't have Q, but we do have PS and PD. Remember, P is PD and PS, I think. Yes. No, sorry. It's PC plus PD will give you this solution. So we have this number, and we have this number. We just got to look for Q, which is water, and we have it right here. Nice. Now, let's do the mass balance in the units just to see what else can we get. Hopefully we get compositions. So we do a mass balance in the crystallizer. Let me go back. Sorry about changing a lot, but it helps. So you can see, this is the crystallizer. FC is entering, R is going out, and PC and PS is going out too. Mass balance, which is here. Nice. Now, we know these two guys, it's 1550, so we have this equation. Let's name it 5. And we do the mass balance over W, which is water, in the crystallizer, of course, because we're watching the crystallizer. Just remember to add these X waters here. You know this one, you know this one, you know... Yeah, actually, you just know the... we know PD, we know FC. No, FC we don't know it. Recycle we don't know it. Good. We are left with this equation mathematically, because once you do math, you will know you have only 2 variables, and you have 2 variables here, but we have 2 equations, 5 and 6, and the variables are F's, the feed in the crystallizer, and the recycle. Let's continue. Let's solve it. We're going to solve for R, and then actually from R you could check the feed in C, but I don't know why I didn't put it. Should be very easy. So guys, just know that you could find, once you have this, let me show you which number you need to substitute. You substitute in 6, please, because you already have the value of R. Or actually you could substitute here, it's also easy. FC will be the recycle plus this, which is about 6, no, 7, 10, something like that. You check it. And now we're going to do a mass balance in the mixture. It's simple. Let me go back. Sorry again. Mixture is here. Enters F, outlet. Oh no. Enters F and R. You can see the arrows going in, and it outlets as FE, feed of the evaporator, which we have here. Nice. We have F1. We have recycle. We only need to look for FE, which is this. So we're not that lost. We have almost everything. Now, I do recommend to check what are you being asked, because you don't need compositions. So why do you waste time looking for compositions? Maybe if you're in an exam, you don't have that much time. Just check. You don't need compositions. You just need flows. The flow of water, we have it. The flow of the solids, we have it. The flow of the the feed in the evaporator, the one I just showed you here before, and the feed we just calculated here of the crystallizer. Now, we have the recirculation, yes. We have the feed, yes. We can do all math, so we just solve that the recycle ratio is 1.25. And this is part 3. What happens if there's no recycle? You will lose all the crystals in the solution. So if you have this operator, you have this solution, which has certain amount of K, and you have solid K. This one is okay, because you just pack it, some package, and you sell it. But if we just throw this, well, it will not be cool, because we're losing K in the form of solution. It's hidden. So the best thing to do will be to recycle 100%. But maybe the process is not able to recycle 100%. That's why they only recycle, I think, 95%. So make sure, guys, you understand the problem. We already answered all the flows. You must solve for the flows, just check them. What else? The recycle ratio is very important. The bigger R in F is, for example, here, the bigger means you're recycling a lot. So this depends a lot of the process, a lot of the products, what do you want, etc. But in general, a good recycle ratio will be something about that, 120 to 180. But I'm telling you, you need to know the process. Maybe they tell you 5,000 times the recycle, which is crazy, but maybe it works. And if it works and makes money, it's fine. And finally, guys, if you need more exercises of bypass and recycle, just go to this webpage and you will find a lot of courses, hopefully. And what else? Yeah, just go to the mass balance course, and if you need problem solved, here are the problem solved. You can have, I think it's about 40 problems for this chapter, which are mass balance with recycle, mass balance with bypass, etc. Nice. So in the next video, we're going to make a break. We're going to see what we have seen before and what are we going to see later. So see you in the next video. What's up, guys? It's me, Chemical Engineering Guy. So if you like the video, why not push the like button? It really helps me to know if you're liking the videos, or if I should be changing something, or I should be adding something, taking out content, whatever. Also, sharing is caring. So if you got any kind of friends, teachers, colleagues, or whatever kind of person that might be interested in this type of content, why not share it? Sharing helps our community to grow faster in members and in content. If you want to keep track of my activity, videos, uploads, experiments, playlists, whatever content I'm getting on YouTube, be sure to click the subscribe button. Subscribing to the channel is totally free, guys. My dream is to create an online academy of chemical engineering, where everyone can access it in the world. Imagine a place in which the student, the teacher, and the engineer get the best of each other. Thank you guys for the support and the love.